Another category of the problems in dynamics are based on the concept of the velocity as well as the relative velocity. Now, relative velocity is a concept where we will be finding the velocity of one object with respect to other. Now, this is a common phenomena. For example, when we are traveling in a car or in any automobile, then we will find that as if we are stationary and the other objects are moving in the opposite direction. Say when we are traveling in a train, then we will find that the trees and the other objects which are actually stationary, they are found to be moving in the opposite direction. Now, this is exactly what is known as the relative velocity. Because if we place ourselves in a particular object which is moving, then with respect to us, that object becomes the stationary object. That means the velocity of the object with respect to us will be 0. And then in that case, the other objects which are otherwise stationary, they are found to be moving in the opposite direction. The concept over here can be shown in this manner. Suppose the train is moving. So we have the velocity for that particular train. And there is some tree. Now, if we place ourselves somewhere here, then we can always see that the tree is stationary and train is moving. Now, when we place ourselves in the train, then what happens is with respect to us, the velocity of the train becomes 0. Now, if velocity of the train is to become 0, we will have to apply equal and opposite velocity so far as the vectors addition is concerned, and the same velocity will be applied to the entire system, even if there is some person standing over here. Then this velocity will be applied to the tree, the same velocity will be applied to the person, and effectively this velocity becomes 0 and the other objects are found to be moving in the opposite direction. So we will be finding velocity of the tree with respect to train. Now, sometimes some other phenomena also comes into picture, that is the observation that if the tree is closer to the train, we can actually see that it is moving with the higher velocity, whereas as the tree is moved away from the train, that tree is found to be moving with the less velocity. Now, this concept we will be dealing in this particular chapter very carefully. The distance phenomena may or may not come into picture. So, the topic is called as the relative velocity. The consideration that we had right now, that was when one object is stationary and other object is moving. What if both the objects are moving? For example, we have some object B moving with some velocity of B, and some other object, say object A, it has got its own velocity as the direction is shown. Now, if we are required to find, say, velocity of B with respect to A, velocity of B with respect to A, this should be read as B with respect to A. That means A should be made stationary. Now, if A is to be made stationary, then we will have to apply the velocity to A in the opposite direction, having the same magnitude, but the same velocity will be also applied to B. So, this is minus VA that we are applying. So, A becomes stationary, and then B will have the resultant velocity, being the vector addition, the resultant velocity of B can be found out by the usual law of parallelogram, and we will find that B is moving in this direction. So, this is velocity of B with respect to A. Of course, this angle also can be calculated we have got the cosine rule, by which the angle made by the resultant with one side of that parallelogram can be very well found out. So this was velocity of B with respect to A. If we are required to find velocity, so here velocity of B with respect to A can be written as velocity of B minus velocity of A. But remember that it is not going to be the scalar subtraction, it is a vector subtraction. Exactly on the same lines, say when this was velocity of B and we have object A, its velocity is VA, and if we are required to find velocity of A with respect to B, then we are required to make B stationary by applying the velocity minus VB, so that net velocity of B will be 0. The same velocity will be applied to A, this is minus VB, and then addition of these two will give us velocity of A with respect to B. And this is a vector addition. Once again, we can write it as velocity of A minus velocity of B. Now these two parallelograms, if you observe, then you will find that these sides are parallel, even their lengths are same. The parallelogram that we draw over here will be almost the identical, but the resultant has changed the direction, and we come to the conclusion that velocity of B with respect to A will be minus of velocity of A with respect to B, and this minus sign is indicating that it is opposite in the direction. So the relative velocity concept is very useful, and then we can also determine some other phenomena like what is the shortest distance between the two objects, because now if B is stationary, then I can find out that the shortest distance between A and B will be the perpendicular, because this is line of action of the resultant velocity. If we just drop a perpendicular, this will become the shortest distance. And how to find this shortest distance? We will have to consider some other concepts, because now this is not the equation of line. We are not going to drop the perpendicular and find it, but we will be using some other concepts over here to find out the shortest distance between two moving objects by the use of the relative velocity. Also that there are cases where the relative velocity will be very much useful to solve the everyday problem. For example, say when we are moving in a train, so if we are moving in a train and there is some tree over here which is a stationary, say tree object, and when we are exactly at this point, say point A, we already have, as we ourselves are in the train, we have got that particular velocity with us. We are moving with that velocity of train, and if we decide to hit this tree by throwing a stone, we want to throw a stone and we want it to hit the tree. Now if we just throw the stone perpendicular to the train, then what happens is, as we are giving the velocity in this direction to the stone, when it is released, it is actually moving with velocity of train also, though for us that particular stone will be stationary at that moment because we are holding it in our hand, but the entire system, that is the stone, ourselves as well as the train, everything is moving with velocity of train. And so when the stone is thrown, actually it has got the velocity of train also, and when you throw it perpendicular to the train, you will find that it actually moves in this direction, because this is the velocity that we are giving and it already has got the velocity of train, so it will move in this particular direction, and you will find that instead of hitting the tree, it falls somewhere here. Now if at all we want to hit the particular tree, then we will have to first of all consider the fact that it already has got the velocity of train. We will have to throw it in such a manner that when we add the velocity of train to it, the resultant should go in this direction. So we will have to first of all set the velocity of that particular stone to 0 with respect to the real world, because it should not be the part and parcel of train. It should not carry the velocity of train with itself. So I will have to have velocity of train over here. And now if I decide to throw it, in some direction like this, this is how the considerations will now apply. But then you will find that to this velocity of train will get added. We don't want that to happen. We want to give the velocity to the stone in such a manner that when, say, if I apply the velocity to the stone in this direction, then this will be the velocity component of the stone along the train direction. Now this component will be numerically equal to the velocity of train. So these two components are just the same. So we are going to throw the stone in such a manner that in this direction, such that its component, if I consider this as horizontal direction, then its component in the horizontal direction should just cancel the velocity of train, and effectively when we add velocity of train to it, it is bound to move in this direction. This is the resultant velocity, and then it is going to hit the particular tree. Now this concept should be used when we are solving the problems using the relative velocity, because now we are required to decide the direction in which the stones should be thrown so that it will actually hit the tree. If we throw it in the forward direction, then it will just fall even beyond that, because the velocity component of the stone is going to add to the velocity of train. We want to cancel the effect of velocity of train, so it should be thrown in the opposite direction, and so effectively it will move in the perpendicular direction. So we have the resultant concept over here, and then accordingly we will solve the particular problem. Another factor could be the case when, say, there is a river and the flow is in this direction. Some boat wants to cross this particular river and reach the opposite bank. The question is, in what direction this particular boat should be actually travelled, or it should be pedalled, so that we will reach exactly point B, which is perpendicularly opposite, that is on the other side of the bank. From A, if we want to reach B, in what direction we should be actually driving that particular boat. So this is velocity of flow that we have. Now this velocity of flow component should be cancelled. The consideration can be given in this manner. We want to travel in this direction. Say if we travel in that particular direction, then due to the flow velocity we will be also shifted in this direction and we will be here. If we actually travel with the boat in the perpendicular direction, then due to flow velocity we will be moving to this position. So we will give a consideration that when we start moving, we will try to move in this direction. Velocity of flow will be added and we will be at this point. Again we will give the next pedaling effect. It will be in this direction. Flow velocity will cancel that. Of course, we are assuming that the flow is the constant velocity from this point to this point, and every time the movement is going to be like this, and we will be actually reaching the point B. Now this is infinitesimally small phenomena that we will have to consider, and we can effectively say that we should be traveling, say, in this direction, so that velocity of flow will be added and we will be reaching point B. So these are the problems which we will be discussing in this particular concept of relative velocity. All the problems will have the same phenomena of considering the velocities of both the objects at one time, making one of the objects stationary, or give the consideration that as the object itself is moving, what is the effect of the velocities which will otherwise be applied to that particular object. Because that object is moving through some media, the object is likely to have some default velocity which is going to be the horizontal velocity, and then that velocity effect has to be cancelled because we know the resultant direction. So let us take some problem and try to solve that problem. Say, consider the first case. It is given to us that there are two planes, and plane A, which is moving due east, say with a velocity of 500 kilometers per hour, with a velocity of 500 kilometers per hour. Plane B is moving due, say, northeast, with a velocity of 700 kilometers per hour. This is the information that we have, and both the planes are at the same point initially when they start moving. So actually they are just one over the other, we can say, and then they start moving in the respective direction. We are required to find the velocity, of plane B relative to plane A. Find velocity of plane B. Find velocity of B with respect to A after 2 seconds. Now in this particular problem, we will have to first of all consider the directions properly. This is the north direction, south direction. Conventionally we will be always showing north upwards. This is east and this is west. Now plane A is moving due east with a velocity of 500 meters, 500 kilometers per hour. Plane B is moving in the northeast direction. This is northeast direction, and velocity of B is given to us as 700 kilometers per hour, and both are at point O initially. Now we are required to find velocity of B with respect to velocity of A. We want to find velocity of B with respect to velocity of A. The formulation will be obviously velocity of B minus velocity of A in the vector subtraction form. So we can start the solution by drawing a point, then by drawing a line at 45 degrees. This is 45 degrees line. This is velocity of B that we have. Velocity of A is to be subtracted, so you will have to draw in the opposite direction velocity of A, and then the resultant is to be found. And so this will be velocity of B with respect to A. But this is going to be the consideration at t equal to 0, at the moment when they are at point O. You will find that plane B is moving in this direction, that it is not moving towards northeast if you are in plane A. Can we calculate this? We have got a formula as resultant. This is a standard formula that we have for a parallelogram having one side as P, other side as Q. If the resultant is to be found out, this is R and this is angle theta between it, then R will be equal to under root of P square plus Q square. It will be plus 2PQ cos theta, where theta is angle between the two vectors P and Q. This is the cosine rule that we have. So the cosine rule will help us to add these two vectors. So in this case, we know that the lengths are, if we are to apply the parallelogram law over here, then velocity of B with respect to A can be calculated, its magnitude can be calculated by under root of 500 square plus 700 square plus 2 into 500 into 700 into cos of 135, and we can get the numerical value. Now he is asking us to find velocity of B with respect to A after 2 seconds. After 2 seconds also the velocity is going to remain the same, because the velocity of B is not changing, it's a constant velocity. Velocity of A is not changing, it is a constant velocity. We can slightly modify the problem and say that velocity of B with respect to A is to be found out, and second part could be, say, displacement of B with respect to A in, say, 1 hour. Displacement of B with respect to A in 1 hour. Now once we get velocity of B with respect to A, of course this is going to be in kilometers per hour, we have not converted it to meters per second. But if we are to find out the displacement, then the formula will be S is equal to ut plus half at square, and we will be using this relative velocity as the initial velocity itself is the final velocity, but that should be converted to meters per second. So convert this to meters per second and substitute. So it is going to be some value, say V1. So V1, this is equal to V1 meters per second, suppose. Then it is going to be equal to V1 into time is going to be 3600 and acceleration is 0. You will get the displacement in meters. Or if you continue with using the same kmph value, then this will be equal to so many kilometers traveled in 1 hour. But this is the approach that we were using, that was rather analytical one. But instead of that, we can go for altogether a different approach, which is called as the vector approach. We will go for the vector approach in this particular case. We will try to express both the velocities in terms of the unit vectors I, Z. This is a plane motion that we are having over here, and the same concept that we have used earlier in case of 3D in statics, the same thing is to be used. I will have y-axis and x-axis. Looking at the original figure, I can express VA as 500I plus 0Z, whereas velocity of B can be written as 700 cos 45I plus 700 sin 45Z, and therefore velocity of B with respect to A will be VB bar minus VA bar. It is going to be 700 cos 45 minus 500 I plus 700 sin 45 Z. So this numerical answer will be available. And therefore magnitude of VB with respect to A will be obviously under root coefficient of I square plus coefficient of J square. And of course the angle also can be calculated. It is tan inverse J component upon I component. So velocity of B with respect to A can be calculated. This magnitude is to be used further when we want to find the displacement in 1 hour. So this was the first type of problem that we will be normally facing. Now another type of problem is the objects, the moving objects are not at the same point. So let us discuss that problem, where the objects have got some distance between themselves at the initial point, and then we are required to determine by relative velocity as what is their movement. It is given that, say, some ship P is moving due east, with a velocity of 20 kilometers per hour. At that time, ship Q is 30 kilometers in south direction with respect to P, and is moving in northwest direction with a speed of with velocity 16 kilometers per hour. 16 kilometers per hour. We are required to find velocity of Q with respect to P. We are required to find the shortest distance between them. And number 3, the time taken to reach shortest distance. Time taken to reach the shortest distance. Now first of all the figure, because without which we cannot proceed. Let us draw ship P. It is moving in the east direction. So velocity of P, which is 20 kmph. This is north direction, south, east and west. Q is 30 kilometers in the south direction. So this distance is 30 kilometers. And that Q is moving in northwest direction. So point Q, and velocity of Q is given to us as 16 kmph. The question is, find velocity of Q with respect to P. That can be very well found out. The shortest distance. Okay, let us first of all find out the velocity of Q with respect to P. The vector approach will be proved to be the easier approach in this case. So we will write Vp in the vector form, and it will come out to be 20I plus 0z. Whereas velocity of q, when we want to write in the vector form, then its horizontal component will be negative. It is in the west direction. So minus 16 cos 45I plus 16 sin 45z. And so velocity of q with respect to p will be vq bar minus vp bar, and it will come out to be minus 16 cos 45 minus 20 I plus 16 cos 45 z. And then of course the answer can be written through the calculations, and you can even determine velocity of q with respect to p, the magnitude. And this answer is again going to be in kilometers per hour. Now if you actually see the diagram, then that diagram is going to be we were having velocity of p towards east, and velocity of q was at 45 degrees. This was VQ, this was VP, and it is VQ minus VP. So this is minus VP, and if we want to add them, then the addition will be like this. And where was point P? Point P is 30 kilometers at this position. This is point P actually, and this is Q. So to Q we are applying that particular velocity, and P is stationary. So this is velocity of Q with respect to P. Obviously from P we can drop the perpendicular, and this is going to be the shortest distance. We are required to determine this shortest distance, and of course the time taken to reach that. So though these two ships, they are moving in some opposite directions or different directions, at one time they will be very close to each other and then they will be departing. So as we try to find out the shortest distance, we will have to take help of simply the trigonometry, because otherwise the problem cannot be solved. So this figure will be useful and not the vector approach. Of course the vector approach will be useful, but provided we find the angle correctly. So let us determine this angle, say angle theta. Can we determine this angle theta? Angle theta can be found out from VQP, because VQP bar we already have it in IJ form, and we know that this is the net I component and this is J component. So these two components we already have. I component is negative and J component is positive. Let us forget the signs and consider the heights, the distances. We can very well find that tan theta is nothing but J component, that is coefficient of J, upon coefficient of I. Take the mod. So you will have the value of tan theta, and you can determine value of theta, so many degrees. Now if this angle is theta, can we determine any angle over here, because this is going to be perpendicular to it. If this is theta, then this is going to be 90 minus theta. This is 90 minus theta, and obviously this will be theta. But this distance is known to us as 30 kilometers. This distance PQ is 30 kilometers, and suppose I call this as point S or point T, then we can very well say that distance PT, which is the shortest distance, is nothing but PQ cos theta. PQ is known to us as 30 kilometers. It will be cos of the angle that we have calculated, and you will get the shortest distance between the two ships as distance PT, that is these many kilometers. Now what the consideration, of course through vectors also it is solvable, but in that case you are required to take the dot product, and that is going to be slightly a difficult job, because then I will have to project one vector along the other vector and then take the dot product, etc. But now through analytical procedure, through this diagram, it will be easier because we are simply solving it by the trigonometry. So first part we solved by the vectors, second part we are solving it by the analytical technique, and that is obviously easier. Now the third part of the problem, which says that time taken to reach this shortest distance, let us call this as d kilometers. Now if this shortest distance, shortest point or the closest point is achievable, and we will be using the equation s is equal to ut plus half at square, and here we will be using the relative velocity, that is velocity of q with respect to p, the magnitude. Acceleration is 0 and the displacement is distance pt, that is d, so into time t. Therefore time t can be calculated because it is going to be d upon mod of vqp bar. But remember that vqp bar is in kilometers per hour, whereas d is in kilometers. The answer that you are going to get is in terms of hours. So these many hours. Of course, if you multiply this answer by 3600, you will get the answer in seconds also. So even the shortest distance problem, it can be solved. And then related to this shortest distance, they can always say that the two ships, there are some problems where it is said that the two ships can communicate when the distance between them is less than say 27 kilometers. So 27 kilometers could be the range of the radar, so that these two ships can communicate. Now observe the fact that we have just now solved the problem where we were finding the shortest distance, and if we try to again observe the same figure that we had drawn earlier, of course I will have to show you the same construction once again. This is minus Vp, we were having Vq, and the resultant of these two, this was VQP, this was point P. This is how we were dropping the perpendicular onto it. But this perpendicular could be a very small distance right now. The distance say of the value say 20 kilometers or so. Then the distance between the two ships might become 27 kilometers. It was initially 30 kilometers. It will become say 27 kilometers at time t1. Then it comes at the shortest distance, and then it again becomes 27 kilometers on the other side, say at time t2. So in this particular portion, the two ships can communicate with each other. So we are required to find, that is, how long they can communicate with each other. In that case, the information that we have is related to the distance, that is not the shortest distance but the distance 27 kilometers. Now this 27 kilometers distance is to be used so that we can find out the corresponding time, and we say that we are likely to get two different answers for the time. Let us see how the equation is to be written. We can again write the same equation, S is equal to ut plus half at square. Of course, this component will not come into picture, acceleration is 0. Now S is given to us as 27 kilometers. U we already have calculated, its component is known. The horizontal U is nothing but mod of VQP bar, that is known, into time t. But then here we will be getting the time t as a single value. We will be getting time t as the single value. But the question is whether we should be considering VQP in this manner, because here we are saying that the distance travelled is 27. This is not going to work at all. It is not the distance that is to be travelled which is 27 kilometers. It is the perpendicular distance which is 27 kilometers. And if the perpendicular distance is 27 kilometers, then we have already calculated this time t, and we know the shortest distance. Let us call that shortest distance, which was, this was point t, so this distance was pt. Now with respect to pt, we can determine, actually taking this as hypotenuse, we can simply construct a triangle like this on one side and the same triangle of course on the opposite side. We already have this distance pt with us. We know that this is right angle, and if I call this point as, say, point R1 and point R2, then we are given that PR1 equal to PR2 equal to 27 kilometers. PR1 equal to PR2 equal to 27 kilometers. Now from PR1 and PT I can find out TR1. So TR1 distance can be calculated. It is going to be under root of 27 square minus the shortest distance PT square, and we can get the distance TR1. Now we can very well determine as what is the time taken for the ship to travel from R1 point to T point. So time taken to travel from R1 to T. So this time can be calculated, because now we can use that distance phenomena as TR1 is equal to mod of VQP bar into time, say T1, and therefore you will get the value of, is it going to be T1? No, it is not going to be T1, it is some time, say T. So let us calculate that time T, which is TR1 upon mod of VQP bar. So in time t, the ship travels from point R1 to T, or over here from T1 to T, whatever is the difference, because we have already calculated time taken to reach the shortest distance. So we have got now the answer as this is going to be equal to, if I call this as T shortest, that is TS, then I can very well say that the time that I have calculated is nothing but TS minus T1, and I can determine value of T1. Rather, this particular time should be added, and subtracted from TS. So we can very well say that therefore the two ships, can communicate with each other from TS minus T to TS plus T time. They can communicate with each other from TS minus T to TS plus T duration. This is the required answer. Now the range that is given to us, that should be used properly, because from here it was 30 kilometers away, then it becomes 27 kilometers from P. then it is at the shortest distance, then it is again at 27 kilometers, and then the distance is more. So the problems are very typical in this case. We should be using the information and then solving the problem using trigonometry in cases as it is applied. But the understanding of the problem is very much essential. Without that, the problem cannot be solved. Let us go for another problem in the relative velocity only. And the problem is given to us like this. A swimmer is swimming at a speed of 4 kilometers per hour. A swimmer can swim at a speed of 4 kilometers per hour. And he wants to cross a river. To cross a river of width 1200 meters. Of width 1200 meters. The flow of the river is 1.5 kilometers per hour. Is 1.5 kilometers per hour. He wants to reach the point on the other bank of river, which is exactly opposite to start point. Find the direction in which he should swim. Number 2, time taken to reach the other bank. Time taken to reach the other bank. And third case, if he swims in perpendicular direction to the flow. If he swims in perpendicular direction to the flow, where will he reach on the other bank? Where will he reach on the other bank? Find the time taken. Find the time taken. Now this was the problem that I was discussing earlier. Now all the considerations were dealt in the earlier discussion. Now what remains is just the numerical solution for the problem. It should be put in the pictorial form. The width of this river is given to us as 1200 meters. The start point is point A, suppose. Exactly opposite point is point B. There is a velocity of the flow given to us as 1.5 kilometers per hour. And swimmer wants to move to point B. Now this is going to be the resultant that we are looking for. So the diagram can be drawn in this manner. That is, this is the answer that we are looking for. We already have the velocity of the flow, and so the swimmer should swim in this direction. So this is velocity of swimmer, velocity of flow. So velocity of swimmer and velocity of flow, they will be added to see the actual velocity. Actual will not be the correct wording, it will be the apparent one. That is how it is going to move. So this is what we will be considering as V resultant. Now if this is the problem to be solved, then velocity of the swimmer, the absolute value is known to us as 4 kilometers per hour. Velocity of flow is known to us as 1.5 kilometers per hour. But what we don't know is angle theta. What we don't know is angle theta, that is angle with which it should actually swim. Now we can write velocity of flow in the vector form. Velocity of flow in the vector form, and it is going to be 1.5 I plus 0 z. Whereas velocity of swimmer can be written as 4 cos theta I, but is going to be negative, plus 4 sin theta z, and therefore V resultant is going to be velocity of the swimmer plus velocity of the flow, as the diagram says. And so it is going to be minus 4 cos theta plus 1.5 I plus 4 sin theta. But we know that V resultant is going to be 0I plus some value into z. And therefore, because resultant is purely vertical, in that case it will not have I component. And therefore we will get minus 4 cos theta is equal to 1.5. Minus 4 cos theta plus 1.5 equal to 0. Therefore 4 cos theta is equal to 1.5, or cos theta is equal to 1.5 by 4, and we can determine theta, angle with which the swimmer should swim. Now once we get this, then we can very well find out V resultant by substituting 4 sin theta z. This is what the resultant velocity. And now with this velocity, if you are to travel 1200 meters, obviously we will come down to find out first of all mod of V resultant, which is going to be 4 sin theta only. Then using the equation S is equal to ut plus half at square, ut plus half at square. S, we know it is 1200 meters. U, we have 4 sin theta, but remember that it is in kilometers per hour. So you will have to convert it to meters per second into time t, and acceleration is 0. And so as theta is known to us, we can very well determine the time taken to cross the river, these many seconds. So the problem can be solved. The first part, it was direction in which the swimmer should swim, that was angle theta, we have already calculated. The time to reach the opposite bank, even that can be calculated. In the third part it is said that, if the swimmer swims in the direction which is perpendicular to the flow, where will he reach on the other side of the bank? Where will he reach on the other side of the bank? Now this is going to be the direction of swimmer, not the resultant. So the swimmer, we will slightly modify the diagram now, because this is going to be V swimmer, and whenever the swimmer is swimming in this direction, he will be always having the effect of the flow, and that flow will be added to it. And so the resultant velocity will be in this direction. This is V resultant. Now in this case, velocity of the swimmer is going to be 0I plus 4J, and velocity of the flow is 1.5I towards right. Velocity of the swimmer is along y direction, it is 4J, and so the resultant velocity we can calculate now. Resultant velocity that we will be getting is nothing but simply 1.5I plus 4J. 1.5I plus 4J. Now with this velocity the swimmer is moving. We can always find out mod of V resultant. We can always find out mod of V resultant, which is going to be under root of 1.5 square plus 4 square. So we will get some velocity which is again in kilometers per hour. Of course, angle theta, now in this case let me call this as theta 1, can also be calculated. Angle theta 1 can be calculated, that is the direction in which the resultant velocity is working. So theta 1 will be simply tan inverse of 4 upon 1.5. It is J component upon I component. So even theta 1 can be calculated. Now once we calculate theta 1, then we know that if we just construct the triangle, this distance is given to us as 1200 meters, and this is the resultant velocity. This is the resultant velocity at an angle of theta 1. So this resultant velocity's vertical component will be responsible for covering the distance, and so the time can be calculated, because it is the distance which is to be travelled only in the perpendicular direction to that of flow. Perpendicular direction to that of flow. And therefore we can say that the time taken to reach other bank is going to be 1200 meters divided by the velocity in the vertical direction, which is 4 kmph. Of course this should be converted, so it is 1200 divided by 4 into 1000 upon 3600, and these many seconds is the time. These many seconds is the time. This is one answer that we get, that is the time taken to reach the other bank. Now where he will reach, because he is going to, resultant swimming will be in this direction, suppose point C, then we are required to determine the distance BC. Where, to answer for the part where he will reach, it is nothing but the distance BC. So BC is to be calculated, and to calculate BC we will consider the same triangle. We know that this angle is theta 1. This is point A, point B, point C, and so BC distance can be calculated because this is theta 1. We can very well say that AB upon BC is nothing but tan theta 1. AB upon BC is nothing but tan theta 1, and therefore BC will be equal to AB upon tan theta 1, and AB is 1200, divided by tan theta 1, you will get these many meters as the distance. So he will not be reaching exactly point B, he will be reaching point C, and that point C is so many meters away from the actual destination. He wanted to reach point B, but he has reached point C. And so we could get the answer of the third part of the problem also, that is, find the time taken as well as where the swimmer will reach if he doesn't take into account the direction of flow of the river. Now the question, as a general knowledge, it is to be asked as whether using the flow is advantageous or using the earlier direction, that is using some direction for the swimmer and then reaching exactly opposite bank, which one of these two will be faster. Of course, now that you are going to perform the numerical calculations, you will be having the value of time also in each case, and then through your judgment or logic you try to answer that which of the two cases would have been effective or faster to reach the other bank. As it appears right now, we can say that if we take the help of the flow, if our aim is just to reach the other side of the bank, then we should be taking the help of the flow and then reaching point C, and that could be faster, and that could prove to be the fastest one, because the resultant velocity in earlier case, in the earlier case in the vertical direction was obviously less than the one which we were expecting. If you just consider the earlier case, then probably the vertical component that we were using, that vertical component was 4 sin theta, I suppose, and that 4 sin theta means that the velocity, net velocity in the vertical direction, that was much lesser than the 4 velocity that we were having initially. And if we use that same velocity 4 as we did in the current case, probably the time taken will be smaller. But of course that is not the part so far as the relative velocity problems are concerned. And so the relative velocity problems can be solved very easily. We can have one or two cases, of course the ones which are to be considered afterwards, once again when we talk about the topic called as the instantaneous center of rotation. At that time again the similar figures will come into picture, but we can very well be asked the questions like this. Say at a particular moment there is a 4-bar mechanism, say drawn in this manner. This is a 4-bar mechanism, say A, B, C, D, and it is given to us that at the particular moment velocity of B is say 10 meters per second and velocity of C is given to us as say 20 meters per second, and the orientation is also given to us that this angle is 75 degrees, whereas if I slightly modify the figure, this angle is 60 degrees, and it is asked to find velocity of C with respect to B. Velocity of C with respect to B. Now if such a problem is asked, we will be first thinking as in this particular problem we are not given any distances. First of all, we don't know length AB, BC, or even CD distance is also not known, AD is not given to us. So how to construct this particular figure? Of course our aim is not to construct the particular figure. We will have to simply remember the fact that these 2 points are hinged, and so AB is going to rotate and CD is also going to rotate. Now if AB is rotating, then B will be having a velocity which will be always perpendicular to the crank, perpendicular to the radius. So this is velocity of B. This angle is 90 degrees. And similarly, velocity of C, as B moves in this direction, C has to move in this direction. and velocity of c is also known to us. Now if you could draw these two velocities, then finding velocity of c with respect to b will be simply the problem of trigonometry. So velocity of b, we can consider its horizontal component and we will require this angle. Similarly for velocity of c, we will be requiring this angle. So it is going to be the calculation based on the angles only. Now of course we can complete the triangle over here, and this is 75, so this is also 75, so this angle will come out to be 15 degrees. Similarly, we can complete the triangle over here. This becomes 60 and this is perpendicular to it, 30 degrees. So ultimately VB bar can be written, which is going to be 10 cos 15I minus 10 sin 15Z, whereas VC bar can be written as 15 cos 30I plus 15 sin 30Z, and then velocity of c with respect to b is nothing but VC bar minus VB bar. We can perform the subtraction and get the required answer. So though the lengths are not given to us, it doesn't mean that the problem cannot be solved. We can still solve the problem. We will have to simply use the logic that as AB link is hinged at A, B point is going to rotate about A and its velocity at any time is going to be perpendicular to AB. Similarly, link CD is hinged at D, and that's why CD link will be rotating about D and velocity of C will be always perpendicular to the link CD. And with this consideration we can find out the angles, because the orientation of the links was given to us, that is to find out the velocities angle made by each velocity, and then using those angles we can write it in the vector form, and through subtraction we can find out the relative velocity of C with respect to B. So these types of problems we are required to solve in case of the relative velocity, and many times the problem will be the real world application, and we will have to determine the time or the distances or sometimes even the shortest distance.